Hi everybody. This is lesson 6. We're going to graph sine and cosine curves today. The graphs of sine and cosine are periodic functions, and that means the function values are going to repeat as x increases. The sine value of a function is equal to the y value at a corresponding point or an angle on the unit circle, and we saw that in our last lesson. And the cosine value is equal to the x value at that same point or angle. So we're going to first look at the graphs of sine and cosine. And I have all of these vocabulary words for walking through the lesson as a general review if you need to come back to them at the end of the video. So let's start by looking at the graph of sine and analyzing that. We know when the angle is 0 degrees, the y value is 0. And when we know that the angle is 90 degrees, the sine at 90 degrees is 1. Then as we move around the unit circle, the sine at pi is 0. The sine at 270 degrees is -1, and the sine at 2 pi, when we get back to the full rotation, we're back at 0. Now, you may not be able to see that this is a nice smooth curve, but if we plotted all 16 points on the unit circle, for example, 30 degrees, sine is a half. And sine is also a half at 150 degrees, which is almost over here to pi. And then sine is -1/2 at 210 degrees, and sine is -1/2 at 330 degrees. So you can start to see how the sine curve is that nice, smooth, oscillating curve. And I won't spend too much time going through the other points, but you get the idea that it's a nice, smooth, oscillating curve. And like we said, it's a periodic function, so this is the first cycle or one period from 0 to 2 pi. That's one complete revolution of the sine curve, plotting the points around the unit circle where y is the sine value on the unit circle. So like we said, this is called the period. So one full revolution. And the stretch is called the amplitude. So the stretch is 1 unit up and 1 unit down. So that's called the amplitude. Amplitude is 1 in this case. And we have a maximum at 90 degrees, a minimum at 270 degrees, and we have zeros at 0, at pi, and at 2 pi. So lots of interesting things that we can see here. And then to write this down, so in the general form, the domain is all reals. That graph continues on infinitely from left to right. The range goes between -1 and +1. So it's bounded above and below. The x-intercepts, if you notice, the x-intercepts were multiples of pi. And if we wanted to write that mathematically, we could say that the x-intercepts occur at pi times a constant 0, where that k value is any integer value, whether it's 0 or 1 or -1, 2 or -2. And if we go back to that graph, you can see that the x-intercepts are at 0 and 1 pi and 2 pi and 3 pi. Or if we went backwards, they would be at 0 and -pi and then -2 pi and so on. We do have a y-intercept, that's at the origin. And if you look at the graph, the maximum, the first maximum is at pi over 2, and the first minimum is at 3 pi over 2. So if you figure every half of a pi, starting with a pi between them, then at 1 pi over 2 and 3 pi over 2, we have a max and a min. So there's going to be another max at 5 pi over 2 and another min at 7 pi over 2. So following those patterns so that we can make some educated type of explanation here, I have a maximum at every pi over 2 plus 2 pi times a constant, and the maximum is going to be 1, and we're going to have a minimum at every 3 pi over 2 plus 2 pi times a constant, and that minimum is going to be -1. Whoop, not a bracket. I need parentheses. It's that writing, talking, and thinking thing. So the function is continuous. It's bounded above and bounded below. And the function is going to have odd symmetry. It'll be symmetric with respect to the x-axis because it's passing through the origin. It's odd. It has symmetry with respect to the x-axis. And the key points, this is my favorite way to graph. So the key points, first of all, I'm going to name them as the pattern. And if you think about the graph, we had an intercept, a maximum, an intercept, a minimum, and an intercept. So intercept, max, intercept, min, intercept. So knowing the pattern, intercept, and then a maximum, and then an intercept, and then a minimum, and then an intercept. Those are the 5 key points that get us one complete revolution or one complete cycle. And on the first period of the sine curve, the intercept is at the origin, the maximum is at pi over 2, the next intercept is at pi, the minimum is 3 pi over 2, and the last intercept is at 2 pi. So we're all the way back to the beginning to have one complete cycle or one period. So that's our sine curve. And that's one of our parent functions. So doing the same thing with cosine, and walking our way around the unit circle, we know starting at 0 degrees or 0 radians, cosine is 1. And then at 90 degrees, cosine is 0. At 180 or pi radians, cosine is -1. And then at 270 degrees, cosine is back to 0. And finally, one complete revolution at 2 pi or 360 degrees, we're back at 1. And looking at where sine is a half, we know at 60 degrees, so that's going to be right about in here, sine is a half. And then at 150 degrees, right about in here, sine's -1/2. And, oh, I take that back, not 150 degrees. I'm thinking sine, not cosine. Let's back that bus back up. Sine's -1/2 at 120 degrees. So that would be right in here. Sine's also -1/2 at 240, which is down here. And sine's back to being +1/2 in quadrant 4 at 300 degrees, so right about in here. And you can see that that curve is, again, oscillating, a smooth curve, and behaves similar to that. So again, it repeats itself every 360 degrees. The amplitude is still 1. and the period is still 2 pi between the beginning and the end of that first cycle. We have one cycle completed in 2 pi radian, or 360 degrees. It also has a maximum at the beginning and the end, and a minimum at its halfway point, and 2 intercepts. Okay? So let's analyze that a little bit. The domain is infinity. It continues on forever. And just like cosine, the range is bounded between -1 and +1. The x-intercepts were odd multiples of half of a pi, odd multiples of 90 degrees. And if we go back, you can see that you're going to have an x-intercept at 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on and so forth. So to write that as a pattern, we would have pi over 2 plus pi times k, and if k is 0, then the first one's pi over 2. If k is 1, then the next one is 3 pi over 2, and so on and so forth. K belongs to the set of integers. The y-intercept was the maximum, that was at 1, and the maximums are going to happen at 0, 2 pi, 4 pi, 6 pi, and so forth. So we have a maximum at every 2 pi times a constant times an integer, and the maximum is at 1 as long as k belongs to the integers. And then the minimums are going to be every odd multiple of pi, so 1 pi, 3 pi, 5 pi in both directions, and we could write that as pi plus 2 pi k -1 as long as k belongs to the integers. Just like sine, that function is continuous. It's bounded above and below, only this time the function has even symmetry, and it's going to be symmetric with respect to the y-axis. And the key points are similar to sine, just different. Instead of starting at an intercept, cosine starts at a maximum. So it looked like this: maximum, intercept, minimum, intercept, maximum, and it oscillated. So maximum, intercept, minimum, intercept, maximum. And those 5 key points on the first cycle, or the parent function, would occur at 0, 1, and then pi over 2 is the intercept. The minimum happens at pi. The next intercept is 3 pi over 2. And then at the end, the maximum is 2 pi. So those are our 2 parent functions for this lesson, sine and cosine. Now, you know, just like anything else that we've done in our course, we like to stretch them, shrink them, flip them, and so on and so forth, or any kinds of transformations. So we can change the height or the amplitude, and we said amplitude is the absolute value of the leading term, and the function, so whether it's sine or cosine, let me jot this down a second. Whether it's a sine curve or a cosine curve, there's a number out here. This is my amplitude. That's what we're going to look at first, the amplitude. And then the argument part, bx minus c plus or minus d. We're going to find out what these values, what the b value, the c value, and the d value do. But for right now, we're looking at graphing amplitude. that's going to change the range of the parent. So here you see I have an amplitude of 2. That means it's going to stretch my graph. So my midline is the x-axis here. And we're going to stretch that parent graph 2 units up and 2 units down. And because the argument is just x, nothing's changing in the parent. We know that we're going to start our graph on sine. The pattern was intercept, max, intercept, min, and then intercept. So we know we have an intercept at the beginning. I like to do mine this way. Let's take care of the beginning and the ending, because we know one cycle is 2 pi. So we've got an intercept at the beginning and the ending. And then if you do the middle term is also an intercept. So in between 0 and 2 pi, our intercept is at pi. And then halfway between the intercept and the intercept, we have a maximum. So halfway on this portion would be at pi over 2, and we have to stretch it by the a value, and the a value is 2. So we have to go amplitude up 2 and down 2. So this point is at pi over 2, 2. And then to do the minimum, we have to stretch that one down. So at 3 pi over 2, the minimum would be at -2. But when we talk about the amplitude, we say the amplitude is 2. And then our job is just to be careful and connect the graph in a smooth, curvy line, not pointy, not V-shaped, but in a smooth, curvy line. So one cycle of the sine of x with the amplitude of 2. Now here's one for you to do. What would happen if you graphed -2 cosine x? If you turn off the camera or the video, you can try this on your own and come back to see if your graph behaves like mine. So we said amplitude is absolute value. Amplitude is 2. And again, our midline is on the x-axis. So we're going to stretch up 2 and down 2. And the pattern for cosine was max, intercept, min, intercept, max. Max, intercept, min, intercept, max. But what do you suppose the negative does to the cosine curve? If you thought about that, you're right. It reverses. The maximum now becomes a minimum, and the minimum now becomes a maximum because there's a negative. This is what the negative does on the 2. So the intercepts don't change because the opposite of 0 is still 0, right? But the negative reflects the graph. This is causing the graph to reflect. And if you graph by the key points, then the max becomes the min, and the min becomes the max. So we want to stretch our graph to, starting out at a minimum. This is our first point. A minimum is also our last point at 2 pi. And then halfway in the middle between 0 and 2 pi, that's a maximum at +2. And then on the first half of the graph, we have an intercept at 90 degrees. Got that out of the way. And then in the second half of the graph, 3/4 of the way, we also have another intercept. And that graph would be a smooth curve with a negative or a reflected cosine pattern, and it would look something like that. Okay, so what can we say about, in both examples, we saw the amplitude was 2, and in general we can say if you have a function where there's a number in front of the sine or cosine, then the amplitude is the absolute value. And when the value of the amplitude is a negative value, how would you describe the behavior? Well, I said that the key points of the maximum and minimum are reversed. The key points of the maximum and the minimum are switched or reversed. What was a maximum becomes a minimum, and what was a minimum becomes a maximum. Okay, so that's one characteristic of a transformation. Now, we can also alter the period. We've already established that the period of the parent sine or cosine is 2 pi. But let's see what happens when the general form of the equation changes the period of the graph. So in this case, we have the sine of 2x. So one thing, to be able to find the period, you've got to get the entire graph to go between 0 and 2 pi, but we're doubling that. So if it's 2 pi is the normal period, and you have double that, then we're going to cut that in half. So we're going to get this value right here in front of the x term. That's going to be labeled our b value in the general equation. And when you want to find the period, you take the normal period of the parent and divide it by whatever b value it is to find out how you have adjusted your period. So in this case, the period has now been shortened, and the period for this particular graph is now going to be pi radians. So you've got to get 2 sine curves in the 2 pi area, if you want to think about it that way. And again, I still want to use that 5 key points. So if sine is intercept, max, intercept, min, intercept, and we have to start at 0 with an intercept, and we have to finish that first cycle with an intercept, but it has to be finished in half the distance, in pi radians. So now, where is the other intercept? It's in the middle of this section, which is going to be at pi over 2. And then our a value, see the a value is 1. Our a value is 1, and halfway in between the 2 intercepts, we're going to go up 1 for the maximum. And then halfway between the other 2 intercepts, we're going to go down 1 for the minimum. So this particular graph, the sine of 2x, completes 1 cycle in pi radians. Now, if you wanted to continue on, I'm going to switch colors. We can just follow that pattern. It's like cut and paste. So we had an intercept here, and then a maximum, and then a minimum, then an intercept, and then a minimum, and then another intercept. So we have a second revolution or a second cycle right there, but it continues on forever and ever. We just don't have graph paper to show that. So if 2x shrunk the graph, what would half of an x do? Using that same reasoning, 2 pi divided by b represents the period, and in this case our b is 1/2. That's my argument. The b value is 1/2. So 2 pi divided by 1/2 makes the period stretch out, kind of slows it down, makes the period 4 pi long to complete 1 cycle. And it's a cosine graph, so our cosine patterns are max, intercept, min, intercept, max, and we have to slow down to get 4 pi in there. The a value, still 1, so my maximum is at 0, 1. My other maximum is going to be out here at 4 pi, 1. Where's our minimum? In the middle. at 2 pi negative 1. And then an intercept, the first intercept is going to be at pi, and the last intercept is going to be at 3 pi. So nice smooth curve. Oh yeah, that's hard to do with my smartboard. But it goes something like that, continuing on forever. So summarizing period, you can describe what happens to the graphs. The periods for each of these two functions is 2 pi divided by b, because one full cycle will be graphed on this interval. In general, we can say if you have a standard form and you have an amplitude times the sine or the cosine with a b value that's not 1 in there, then you can find the period by taking 2 pi divided by b. And if we compared and contrasted what happens to the period when b is bigger than 1, or when b is a fraction between 0 and 1, we can go back and look at our graphs and say that when b is bigger than 1, it shrunk the graph horizontally. So I have a horizontal shrink. But when b was a half on the second graph, that was a value between 0 and 1, then that stretched the graph in a horizontal fashion. Okay, so we got a horizontal shrink or a horizontal stretch. So another characteristic. Next, let's talk about phase shift. A phase shift for a trig function is a horizontal transformation from the graph's original starting point. So let's look at that. In this example, we have a sine curve and we have x minus h. So just as we used to do in algebraic equations, whenever you have x minus some value, we remember or recall that this was a shift to the right, where x plus h or x plus some value would be a shift to the left. So in this case, we're going to follow the sine pattern, but instead of starting at 0, we're going to shift pi units to the right. That's going to be my starting point. So we're going to start right pi. And if you think about the period is 2 pi divided by b, and our b value is 1, then if you add the starting point to the period, you'll get the stopping place. So that way you can think about the pattern as intercept, max, intercept, min, intercept. And instead of starting at 0, we're going to start at pi. And instead of stopping at 2 pi, we've got to stop 3 pi because the period is 2 pi for one complete cycle. So if we start at the intercept at 1 pi and we stop at an intercept at 3 pi, then in the middle is our other intercept. And like we said, the a value is 1, so we're going to stretch 1 up and 1 down, and we're stretching a maximum at 1.5 pi and a minimum at 2.5 pi. So this is my 1 or parent function, or my first cycle of that sine curve that has a phase shift of pi units to the right. So if you are being asked to draw more than one complete cycle, then you could do that by, again, cut and paste. So if we stopped here, if we did intercept min, intercept max, intercept, if you follow that pattern, min, intercept max, intercept min, intercept max, intercept min, intercept, you can just fill up that entire piece of graph paper showing more than you need, that it's continuous. And then I'm sure the next one is going to have a phase shift to the left. Yep, so this is going to start, we're going to start our graph at negative pi. The complete cycle for cosine is 2 pi. So where do we stop? We'll stop at positive pi. So start at negative pi. Cosine is max, intercept, min, intercept, max. And we're starting at negative pi and stopping at positive pi. So what will that look like? A maximum at negative pi, where the amplitude is 1 and the period is 2 pi. So we're going to start at a max and stop at a max. And in the middle is a minimum. In the first half, there's an intercept. In the second half, there's an intercept. And this is our first cycle. It's not a V, it's a curve. It's a curve. So that's the first cycle. And again, switching colors, we're going to have max, intercept, min, intercept, max, intercept, min. And you can fill in that graph paper with an oscillating function. And you can fill in the graph paper in the other direction with an oscillating function. And graph more than one complete revolution. So again, summarizing, in both examples, the phase shift is pi. It won't always be that way, but these are our basic ones to start. In general, we can say if our function looks like this in standard form, sine or cosine, then the phase shift can be c over b. When the argument is bx plus c, we shifted the graph to the left. But when the argument is bx minus c, the phase shift goes to the right. Okay? And then we can also move that midline, that vertical shift. That's going to be the letter D. If you add or subtract a number to the entire equation, you can shift a trig graph up or down. And this is a shift in the x-axis, and it creates a new midline for your graph. So here in this case, you see we added 1. It's not saying sine of x plus 1. It's not like that. Don't confuse that. This is the sine of x, and then add 1 to that graph. So we've translated the graph up. This is called my D value. So it makes my midline at 1. This is the midline. So we could come over here and draw maybe a little new x-axis in a dotted line. I'm going to do that in red so I can pay attention. Otherwise, I might make a mistake. Actually, let's just label it. This is, we'll call it x prime. Instead of using the black x-axis, I'm going to use this dotted x-axis, which is my new midline. But just as before, the regular sine curve, we still have the period is 2 pi, the amplitude is 1. If we start at an intercept and stop at an intercept, and the period is 2 pi, so we could write that down. A is 1, 2 pi over b is 2 pi, and the d value is 1. So halfway in between, intercept, max, intercept, min, intercept, and we have a stretch of 1 for a max and a min following that pattern. And that graph continues on. So you can change the midline by adding a number or subtracting a number. Here's one for you to try. So cosine of x minus 2, put your new midline at negative 2. I'm calling that x prime. And cosine starts at a maximum and ends at a maximum and has a minimum in the halfway point and an intercept in between. So your new cosine of x has been shifted down 2 units since our midline is now at y equals -2. So summarizing all of that, this is the important part. Anytime you see a sine curve or a cosine curve written in standard form like this, it's the d value, that number outside of the argument, either added or subtracted. That's your new midline, and you have to be careful for that. I believe that's the end of our lesson. Next time we'll graph tangent and cotangent and some of the reciprocal functions. Until then, bye.